the results you would have gotten in the last activity are going to be characterized in one of two ways. Sometimes the limit of this integral will be finite, sometimes it'll be infinite, and sometimes something weird happens and you can't even determine what the limit is. Considering these different possibilities, we're going to use the word converges if the limit of that integral exists and is finite. If the limit is infinite, or we just can't find it because it doesn't exist, then we say that the integral diverges. For simplicity in this class, we're going to focus only on improper integrals where the integrand is non-negative. So we're not going to be thinking about what happens when a curve dips under the x-axis and contributes negatively to the area under the curve. So another thing to observe that's really important is if the function itself, not even the integral of it, just the actual function, the actual graph, the y values, if those y values don't approach 0 eventually, in other words, if limit as x approaches infinity of f of x isn't 0, then there's no way that the integral, where we're in a sense adding everything underneath the curve, there's no way for that to converge to something finite. Okay, so we do need to watch out for that to help us decide whether or not an improper integral will converge or diverge. But again, this isn't saying that if this limit is true, equal to 0, then this will converge. That doesn't guarantee it, but we just know if this integral converges, we know that we had to have this limit as x approaches infinity of the actual function being equal to 0. It's not saying the integral is equal to 0. Bear that in mind. Okay. So you're going to be practicing your integration skills, and you're going to be combining it with this idea we've been talking about when you're setting up how to calculate an improper integral. So practice your integration skills on each of these integrals. You may need to use the techniques we've been using in this class to do some of these. But remember, you have to make these infinities a single letter. Usually we'll use b for that letter. And then after you calculate that integral where you're going to have some formula with b in it, you're going to let b go to infinity and see what happens. Part F is the most important of these. My tip for part F is to keep in mind that there's a difference between p being between 0 and 1 and p being actually equal to 1 and p being greater than 1. Think back to the activity you did over here. Notice that the first integral you did in this activity is the case where p equals 1. The second integral you did is in the case p is greater than 1, which means you might need to make up an example by picking a number between 0 and 1 since you didn't already do one of those in this activity. That's my hint for activity 6.5.3. Please pause the video, give all of these integrals a try. It never hurts to practice integrals more. So please do that before you proceed. Okay. So there's a second type of improper integral, and this one is a type that involves unbounded integrands. In other words, the functions that we're integrating are unbounded in some way. Okay, let's consider for the moment the integral from 0 to 1 of 1 over square root of x dx. Notice that this is not an unbounded interval, but what's going to happen is we're going to have that this integrand is in some way unbounded. And how do we know that? Well, this function has a vertical asymptote at x equals 0. So it's not technically continuous on the closed interval 0, 1. But again, this idea of taking a limit of an integral is what we're going to use to help us figure out if we're going to get a finite area or not under this curve. So we need to just back away from 0 a little bit. In other words, for this picture, our lower limit of integration is going to have to be some letter a. We'll call it a. And we want to let a, after we've calculated the integral with a as our lower limit, we want to let a approach 0 so that we get to a situation that's more like this picture. Okay, so again, what are we doing? We're going to calculate the integral from a to 1 of this function. We're going to get some formula that's in terms of a now, and then we'll let a approach 0 from the right. That's very important because it might behave differently approaching from the left. It might not even be defined approaching from the left. So we do have to keep that in mind. Okay, so again, we do this by what I just said. Here it is in formula form. When we evaluate the integral from a to 1 of 1 over square root of x dx, and then take the limit, that will give us our conclusion. So let's see what happens when we go through these steps. We write the integral from 0 to 1 of 1 over square root of x dx as the limit as a approaches 0 from the right of the integral from a to 1 of 1 over square root of x dx. We do the calculation, plug in the limits of integration. Now, as I've been saying, we have a formula in terms of a, and now we're taking the limit of it as a goes to 0 from the right. Turns out that this limit is equal to 2, which means this integral converges to 2. So again, what this is saying is that this area is finite. This area is actually equal to the number 2, which is kind of crazy if you think about it. Why should it be 2? Something so simple. But that's the way it turns out.